Good morning, everyone. I'm Zhao from Jilin University and the University of California, Riverside. Today, I'm excited to present our work, FlexPipe, a framework designed to maximize training efficiency for transformer-based models with variable lines inputs. Here is a brief outline of today's presentation. I will start with the background and motivation behind our work, then dive into FlexPipe's insight and design, and finally present our evaluation results. Transformer-based models are crucial for large language models, but their training often faces efficiency challenges due to variable lines inputs. As shown in the first graph, the sequence lines distribution demonstrates significant variation. Traditional methods pass shorter sequence to a fixed maximum lines, leading to a wasted computation and memory. While some approaches aim to mitigate this, they primarily optimize within a single iteration. The other two graphs clearly illustrate this inefficiency. Comparing fixed lines with variable lines training for BERT large and GPT model, we could see a significant reduction in throughput for variable lines, leading to a wasted computation and memory. We could see a significant reduction in throughput for variable lines input across different optimization methods. On the other hand, the scale of transformer methods is growing so fast as seen in the figure. For instance, training DeepSeek V3 demands 2,048 H100 GPUs for 55 days. To handle this, various parallel schemes are employed, including data parallelism, pipeline parallelism, and tensor parallelism. Our work primarily focuses on the elasticity of pipeline parallelism, which is widely adopted due to its lower communication overhead. However, existing distributed frameworks typically use a fixed number of devices with a static parallel strategy based on the maximum sequence lines to avoid out-of-memory errors. The left graph, The left graph illustrates the computation efficiency and memory usage when training GPT on variable lines inputs. We observed significant fluctuations across iterations with low average computation throughput and memory utilization. The right figure showing training time under different sequence lines on varying number of GPUs highlights that the optimal number of devices changes with sample lines. Given that most iterations in variable lines training consist of short data samples, static strategies severely degrade overall throughput. Our core insight is flexible training. FlexPipe dynamically adjusts the parallel strategy during training to adapt to the variable lines of transformers in each iteration. This involves selecting the appropriate number of devices and configuring pipeline parallelism, and crucially, utilizing any idle GPUs to increase the degree of DP. Figure shows how FlexPipe can shrink PP stages from 4 stages to 2 stages, then grow them to 3 stages for different lines of input with different memory requirements. This dynamic adjustment presents two main challenges. Firstly, dynamically adjusting PP stages introduces a huge overhead. Existing frameworks use suspend, resume, or iteration stalling, which cause long stalls due to initialization and communication. Secondly, frequent reconfiguration or an improper parallel strategy would still degrade performance. We need to determine when to adjust PP and how to find the optimal parallel strategy to maximize throughput. To address these challenges, we designed a framework, FlexPipe, as a middle system between a typical training system and its underlying execution engine, dynamically adjusting the number of PP stages and configurations. Our architecture comprises 3 main modules: monitor, planner, and twin layer manager. A key innovation in FlexPipe is our live flexibility mechanisms, called LFIM for short, which transparently adjusts the number of PP stages and configurations without stalling. The core idea is to reduce initialization overhead and overlap communication and computation. As shown in the left figures, when adding a PP stage to mitigate memory pressure from longer sequence, new DP instances are introduced. Initialization steps for PP and DP are executed, overlapped with data transition. After backward propagation, updated parameters are sent to duplicated layers in host memory, and new parameters are copied in a pipelined manner for the next iteration. The right figures shows how to remove a pipeline stage. When reducing a PP stage for shorter sequences, data redistribution is needed. After backward propagation, parameters of deleted layers are directly removed from devices as all. This is because all DP instances maintain identical model parameters. This results in significantly lower overhead of LFI compared to non-live migration approaches. To efficiently perform LFI and maximize training throughput, we formulated a new optimization problem. The flexible memory optimization problem, we called FMOP for short. This problem considers multiple memory optimization techniques and flexibility mechanisms to avoid unnecessary reconfigurations. The FMOP seeks to minimize the total iteration time by finding the optimal memory optimization scheme and mapping of stages to device groups. To solve the NP-hard FMOP problem, we designed a heuristic bound search algorithm called HBSA for short. HBSA consists of three main parts. The first is computing the bounds. This step identifies the minimum number of devices required to filter out invalid mappings. The second is navigating efficient mapping. The search function uses these bounds to get a recursive search for efficient mappings of stages to device groups. Finally is determining triggering timing. Once an efficient mapping is identified, we use the conditions demanded earlier to decide whether to trigger the LFIM. In this slide, we provide an example of how HBSA's triggering conditions work. The figure illustrates 4 types of solutions. For example, in memory optimization strategy 2, increasing the maximum sequence length pushes GPU memory usage to 260 GB, triggering an out-of-memory error. Here, reconfiguration overhead exceeds that of memory optimization. Specifically, in stage S1 prime, the recomputation reduces activation memory by 14 GB, coupled with memory swapping that decreases optimizer memory by 4 GB. We conducted comprehensive evaluations of FlexPipe. We compared FlexPipe against DynaPipe, flash attention, and zero bubble, which represent different optimization perspectives. Our test bed consists of 8 servers, each equipped with 4 NVIDIA A100 GPUs. We evaluate FlexPipe using variants of BERT and GPT models as detailed in Table 1. FlexPipe significantly outperforms state-of-the-art methods in terms of averaging training throughput. Across different maximum sequence lengths and global batch sizes, FlexPipe achieves an average of 1.25 times higher training throughput than SODA frameworks. The top graphs show throughput across different maximum sequence lengths. FlexPipe achieves 40% and 22% higher throughput than zero bubble and flash attention respectively. The bottom graphs illustrate throughput under different global batch sizes. FlexPipe and DynaPipe show faster improvement with larger batch sizes because they can support dynamic distribute training, making adjustment overhead relatively smaller. FlexPipe also demonstrates better performance as model size increases. This is because larger models offer more optimization opportunities due to greater fluctuations and device mapping possibilities. We also compare the overhead of different mechanisms as shown in the top graphs. For different maximum sequence lengths, we could see that FlexPipe reduces training time by 35%, 23%, and 19% compared to the suspend resume, iteration stalling, and the FlexPipe without twin layer. This is due FlexPipe's optimized initialization time through twin layer and fine-grained computation, communication, or leap. FlexPipe also shows better performance with increasing maximum sequence length as it effectively handles more frequent fluctuations. The bottom graph provides detailed overhead under different environments, while other methods degrade across nodes due to communication bandwidth. FlexPipe maintains a minimal increase in overhead due to its elaborate overlap. The evaluation studies are conducted to further highlight the effectiveness of FlexPipe's components. The left graph shows that FlexPipe achieves an average of 32% higher performance than FlexPipe without IM. The FlexPipe without IM means a version excluding recomputation and memory virtualization. This demonstrates the importance of integrating other memory optimization techniques, especially when memory fluctuations are moderate, as their overhead is less than frequent flexibility adjustments. The right graph compares the overhead of HBSA with a brute force search version, that is, HBSA without bound. HBSA achieves a significant reduction in overhead, with an average overhead of 15 milliseconds compared to 745 milliseconds for HBSA without bound. While HBSA's overhead increases with model size, it remains reasonable and manageable. In conclusion, this work makes the following contributions. Firstly, we first introduce a flex pipeline parallelism framework, FlexPipe, that improves the efficiency of variable lines training by enabling the IOFM of PP. Secondly, we propose a novel flexible memory optimization problem, aiming at maximizing the training efficiency by dynamically reconfiguring the parallel strategy and utilizing the redundant GPUs across different iterations. Then we design HBSA to solve the optimization problem, while striking a good trade-off between computational efficiency and memory usage. Finally, extensive experiments are conducted to evaluate the efficiency of FlexPipe. The results show that FlexPipe achieves an average of 1.25 times training throughput compared with SODA frameworks. Thank you for your attention. I'm happy to take any questions. You can contact me at the following